Hello everyone and welcome to St. Andrew's Institute of Technology and Management, Gurgaon, Delhi NCR. St. Andrew's Institute of Technology and Management is a very beautiful college. It is one of the best college in entire India. It offers a variety of courses to choose from. BTech, BBA, BCA, and also starting with MBA, Law and Architecture. This is the best college. It provides 100% placements. It has best industry standards and it is one of the best in each and every field. This is the best career choice that you can make for your child. The subject that I shall be taking in this video is Principles of Software Engineering. Code is CSE 302F. This is a CSE 6th semester subject. The syllabus is in accordance to MDU University Rohtak. The topic is our effective modular design, that is functional independence, meaning cohesion and coupling, the design heuristics for effective modularity, the design model, and the design documentation. I, Shalini from CSE department, shall be taking you forward. Functional independence. Functional independence means that when a module focuses on a single task, it should be able to accomplish it with very little interaction with the other modules. That is, modularity has to be maintained. The functional independence occurs where modules such as a package or a class address a specific and constrained range of functionality. The modularity is based upon the functionality, right? So when it is based upon the functionality, so the particular modules will actually be taking care of that particular functions, and this function will be independent from all the other functions or all the other modules, right? So it has a specific constraints, right? By constraining their functionality, the modules require the help of fewer other modules to carry out their functionality. The functional independence of a module can be judged using two concepts, that is, cohesion and coupling. Cohesion is the degree to which a module performs only one function. Coupling is the degree to which a module requires other modules to perform its function, right? So cohesion is when you are performing your own function, and coupling is what you require from the other module to perform your function, right? So cohesion is, it's kind of very local to the functional, wherein coupling is wherein it is interacting with various other functions. The goal of functional independence is to maximize cohesion while minimizing coupling. So you are maximizing the cohesion part and you are minimizing the coupling part. The goal of functional independence is to maximize cohesion while minimizing coupling. The functional independence makes modules easier to develop and test, right? So you can make small modules with small functionalities, and then you can test them individually, and you can also develop them individually. So it gives you very easier way to develop and testing. The changes that you make to how they perform their function are less likely to affect the software as a whole. Functional independence is one of the goals of using information hiding and modularities, right? So the objective behind modularity and information hiding is to obtain functional independence. So see, we can see it with an example. See, there can be no good information hiding if the software has been broken down into modules, not been broken down into modules, right? So if the software has not been broken down into modules, they cannot ever be functional independent modules. If it is not broken into modules, you cannot have functional independence. To have functional independency, you need to break it into modules. And if no information is hid from other modules of the software, if every module always depends on all the other to perform its function, so any change that you made to the software will result in change in having made elsewhere in the software to handle these changes, right? So whatever, like, you make a change to the particular program and the entire program will change, right? So when you're doing with the modularity, you only change that particular modules, and then you see that which places that module is affecting to, right? I hope this is clear. So first we discuss coupling. Coupling is the measure of the degree of interdependence between the modules, as we already discussed, and a good software will have low coupling. So because why? Because it is like how much dependence it has on all the other modules. So we have various sorts of coupling, starting from the worst, that is content coupling, common coupling, external control stamp, and data coupling, which is the best. So we look at it one by one. Data coupling. If the dependency between the modules is based on the fact that they communicate by passing only data, then the modules are said to be data coupled. So what do we say that if the communication is only based upon the data. So in here, the components are independent to each other and the communicating through data. Module communication don't contain tramp data. Example, customer billing system. Stamp coupling. In stamp coupling, the complete data structure is passed from one module to another module. Therefore, it involves tramp data. It may be necessary due to efficiency factors. This choice made by the insightful designer, not a lazy programmer, right? So you pass the complete data structure from one module to the next. Control coupling. If the module communicates by passing control information, then they are said to be control coupled. So what are you passing? You are passing the control information. It can be bad if parameters indicate completely different behavior, and good if parameters allow factoring and reuse of functionality. Example, the sort function that takes comparison function as an argument. Next we come to external coupling. In external coupling, the modules depend on other modules external to the software being developed or to a particular type of hardware. So what you do in external coupling, the modules, they depend on other modules, and these are all external to the software that you are being developing, right? So common coupling is when you have shared data such as global data structures, and the changes in global data means tracking back to all the other modules which access that data to evaluate the effect of the change. So you are basically seeing what is the effect of the change and you're tracking all of them. So it has good disadvantages like difficulty in reusing modules, reduced ability to control data access, and reduced maintainability, right? The last is the content coupling. In a content coupling, one module can modify the data of another module, or control flow is passed from one module to the other module. So how the control flows from one module to the other module, and this is the worst form of coupling and should be avoided at all. Next we come to cohesion. Cohesion is the measure of the degree to which the element of modules are functionally related. It is the degree to which all elements directed towards performing a single task are contained in the component. Basically, cohesion is internal glue that keeps the module together. A good design will have high coupling, high cohesion. So, for a good programming, you need to have low coupling and high cohesion. So the best one is the function, and then it further decreases to sequence, communicational, procedural, temporal, logic, and coincidental. So what are the types of cohesion? First we come to functional cohesion. Every essential element of a single computation is contained in the component, right? So a functional cohesion performs the task and function. It is an ideal situation. Sequential cohesion. An element outputs some data that becomes the input for other element, that is data flow between the part. It occurs naturally in functional programming languages. Communicational cohesion. Two elements operate on the same input data or contribute towards the same output data. Example, update record into the database and send it to the printer. Procedural is wherein the elements of procedural cohesion ensure that order of execution. That is, actions are still weakly connected and unlikely to be reusable. Example, calculate student GPA, print student record, calculate cumulative GPA, and print cumulative GPA. So it's a procedural cohesion. Temporal is where the time is involved. So a module connected with temporal cohesion, all the tasks must be executed in the same time span. So this cohesion contains the code for initializing all the parts of the system. Lots of different activities occur all at n time. Next we come to logical cohesion. The elements are logically related and not functionally. So example, a component reads input from tape, disk, and network. All the code for these functions is in the same component. Operations are related but the functions are significantly different. Coincidental cohesion. The elements are not related, that is unrelated. The elements have no conceptual relationship other than location in source code. It is accidental and the worst form of cohesion. Example, print next line and reverse the characters of a string in a single component. Next we come to design heuristics for effective modularity. See, once the program structure is developed, so effective modularity can be achieved by applying the various design concepts. And the program structure can be manipulated according to the following sets of heuristics. What are they? The first one is obtain the first iteration of the program structure as to reduce coupling and increase cohesion. So what do? You are iterating the first program structure, and you're trying to reduce the coupling, and you're increasing the cohesion. So after developing the program structure, modules may be exploded or improve modules in independence. An exploded module results in partitioning the logic into separate program. An imploded module result in the creation of two or more modules. Next is we try to minimize structures with high fan out, strive for fan in as depth increases. That is, we try to avoid the pancake structure in which all the modules are under the control of a single module, like as shown in figure. So we try to minimize this because 1, 2, 3, 4, 5, 6, all 6 modules are under only one control. So we try to stag out it, right? So what we do to avoid such type of pancake structure, a more reasonable distribution of control is required. Like this is okay. Like B, G is by E and F. So this like if B fails, so not the entire things fail. So we try to do this thing. We try to fan out in a way. Next is keep the scope of effect of a module within the scope of control of that module. So the effect of that modules will be the control within that module. That is, if anything goes change, anything change is required into a particular modules, what you will do, you will change within the system. That is, the scope of a particular module is defined as all modules that are affected by a decision made in this module. The scope of control of all the modules that are subordinate of a module. Then what you do, you obtain the module interfaces to reduce complexity and redundancy and improve consistency. That is, interface designing should be like so that information can be easily passed and consistent with the function of a module, right? Then we define modules whose function is predictable but avoid modules that are overly restrictive, right? So a module is predictable when it will be produced irrespective of the internal functionality. So if whatever happens into the inside of the modules, if you have to be, you don't have to be predictable about it, and there should be much restricted modules that should be avoided. Last is strive for controlled entry modules by avoiding connections pathologicals. Software is easier to understand and therefore easier to maintain when modules interfaces are constrained and controlled. Pathological connections refer to branches or references into the middle of a module. Next, we come to the design model. A design model in software engineering is an object based picture or pictures that represent the use cases for a system. Or we can say, to put it another way, that it is the means to describe a system's implementation, and the source code is a diagrammatic function. So, whatever the system is going to do, first we are going to represent it diagrammatically, right? So, the design module, we can say the design module is an object model describing the realization of use cases and serves as an abstraction of the implementation model and its source code. So what you do, you describe the realization of use cases that serves an abstraction to the implementation model and its source code. The design model is used as essential input to activities in implementation and test. This type of representation has a couple of advantages. First, it is a simpler representation than words alone. Second, a group of people can look at these simple diagrams and quickly get the general idea behind the system, right? So what you do, first you have a simpler representation by words, then you get a group of people and you look at the simple designs and you get the idea, and in the end you, like, we can say that a picture is worth 1,000 words. So you try to kind of gather all of them and you try to design a final model for it. Okay, then we come to design documentation. See, IEEE refers software. See, anything, software, when we did from the starting into our first lecture that we discussed from Unit 1, we said that software is program plus documentation. Right, so design, every stage has documentation. The requirement has documentation, that was in SRS, software requirement specification, and this also, like design also has to be documented, right? We did it earlier also. So, and this documentation is very very important. So IEEE defines software design documentation as a description of software created to facilitate analysis, planning, implementation and decision making. This design description is used as a medium for communicating software design information and can be considered as a blueprint or model of a system. First is scope. This identifies the release or version of the system being designed. The system is divided into modules, that is, the relationship between them and functionality will be defined. Every iteration of the SDD document describes and identifies the software modules to be added or changed in a release. Next is references, that is list of references, both hardware and software documents and manuals used in the creation of SDG that may be of use to the designer, programmer, user or management personnel. This document is also considered useful for the readers of the document. In this section, any references made to the other document, including references to related project documents, especially the SRS, are also listed. The existing software documentation, if any, is also listed. So you have all the list, both hardware and software. Then it is definition. So this will contain all the technical terms that are used in the documentation with their definition. Next is purpose, as to what is the purpose of this document and what is the intended audience. So what it strive to do, what it strive to achieve. That is primarily for individual who will be implementing the system. Next is design description. The actually this comes in the form of white papers, right? So whatever white papers comes from the industry, they are all basically this documentation part. Design description information content, that is introduction, design entity and design entity attribute. So all the description of the information will have all the entities that you took in into the design model, and these entities will be introduced and they will have their attributes. Design description, organization and design views in the end. So we come to an end of it. The first is, what is functional independence? What I think the most important question that comes in cohesion and coupling, I haven't seen any other kind of question coming from there. Sometimes design documentation can be asked, but that will not be a big question. Similarly, heuristics also I've never seen being asked. So you concentrate in cohesion and coupling, and I would still advise that you study the difference between the two also, right? So that's all for today. Take care.